Now we're going to look at graphing a vector function in three-dimensional space. This is one of the more common three-dimensional vector functions that we'll see. The graph of something that looks like this turns out to be a right circular helix. Now, as a reminder, any vector function is going to have an input that is a scalar quantity, and the output is going to be a vector. And I'm going to switch over to pointy bracket notation so that when I plug in t is equal to 0, I'm going to get the cosine of 0 is 1, the sine of 0 is 0, and then when I plug it in t is equal to 0 here, I get the z component that is also 0. So input the scalar quantity t is equal to 0, and the output is going to be a vector. As a matter of fact, it's a unit vector that is going to initiate at the origin and terminate at the ordered triple 1, 0, 0. As a reminder, also, when we have a vector function, we get for free the parametric equations of this space curve. The x parametric equation is going to correspond to the x component of the vector function. The y parametric equation is going to correspond to the y component of the vector function, and the z parametric equation corresponds to the z component of that vector function. So all those parametric equations can be extracted straight from the vector function. The relationship between x and y on this space curve can be more easily seen if we look at the projection of this space curve into the xy plane. So let's consider a light that is shining down on the space curve. A little bit of a spoiler is that it turns out to be a spring-like curve. If we were to project that curve into the floor or into the xy plane, we would see that relationship between xy turns out to be a circle. We see and recognize these parametric equations, cos t, sine t, as being the parametric equations for a circle centered at the origin with a radius of 1. So whatever this curve turns out to be, this circle is its shadow. So if the shadow of that space curve is a circle, that means that space curve is going to have to lie on the outside of a right circular cylinder centered at the origin. So in order to get more information about how this helix is wrapping around the outside of the cylinder, we're going to need to plot points again. Now let's let our table of values overemphasize the fact that the independent variable is a scalar quantity and the dependent variable is going to have an output that is a vector. We already saw that if we plugged in 0, we get the output vector that is 1, 0, 0. Let's see what happens if we plug in pi over 2. Well, plugging in pi over 2 to the x component, we're going to have the cosine of pi over 2, which is 0, the sine of pi over 2, which is 1, and pi over 2 is the z value, so that just gets put in the z component position. So let's let the value of the parameter be pi, and then we'll plug pi into the x component. The cosine of pi is -1, the sine of pi is 0, and pi itself is the z component. And one more, we'll do 3 pi over 2 here. The cosine of 3 pi over 2 is 0, the sine of 3 pi over 2 is -1, and then 3 pi over 2 is the z component of that vector. So we've already graphed the vector r evaluated at 0. Let's now graph the vector r evaluated at pi over 2. When r is evaluated at pi over 2, we're going to have 0 as the x component, 1 as the y component, and then pi over 2 as a z component. So my ordered triple is going to be somewhere up here, and my r vector, r evaluated at pi over 2, is going to be a position vector pointing to that spot. That's the position of our particle on the space curve when time is equal to pi over 2. When time is equal to pi, the position of our particle on the space curve is going to be -1 in the direction of x, 0 in the direction of y, and pi in the direction of z. So that's going to put me back and up a bit. So again, my position vector is going to be my r vector evaluated at pi, terminating at the ordered triple, -1, 0, pi, and this is another ordered triple on the outside of the right circular cylinder. Let's see if we can start to figure out how this is spiraling around. It is going to be a right circular helix, and it's going to be traversing the path, moving around the outside of this right circular cylinder in this direction. So the orientation of this helix is given by these black arrows. So let's see what happens when we change the x and y components to being sine t first and cos t second as the y component. Remember, when we were graphing circles in two-dimensional space, if we had a vector function where the x component was cos t and the y component was sine t, that didn't change the path itself if we were to switch the components. The only thing that changed was the orientation. If we had cos t as the x component, the orientation started in this direction, moving counterclockwise around the circle. If we switch the x and the y components, we ended up with still a circle centered at the origin radius 1, but now we were going to move clockwise around the circle. So the only thing that changed was the orientation. However, if we're in three-dimensional space, we get a completely different path. It's still going to be a right circular helix, but the starting position is a totally different spot. So let's take a look at another table of values. We have our parameter t, our output is a vector. So when we plug t is equal to 0 in for the parameter, we're going to get the vector function evaluated at 0, which gives us a vector. Sine of 0 is 0. Cosine of 0 is 1, and when we plug t is equal to 0 into the z component, we just get 0 as an output. Let's grab one more, pi over 2. When we plug pi over 2 into the vector function, what we end up with is the sine of pi over 2, which is 1. Cosine of pi over 2 is 0, and when we plug pi over 2 into the z component here, we just get pi over 2. And what that tells me is that we'll have our first vector, our initial vector, is going to be pointing to 0, 1, 0. 0 in the direction of x, 1 in the direction of y, and 0 in the direction of z. So our right circular helix has a different start position. When we plug in the value pi over 2 for the parameter, we get 1 in the direction of x, 0 in the direction of y, and pi over 2 in the direction of z. So that's going to be kind of up here. Again, we're on the outside of a right circular cylinder, but what this begins to look like is a right circular helix, but this time it's going to be going around that right circular cylinder in this direction. Again, we indicate the orientation with these arrows, and this is an entirely different space curve than the one we had before. Let's verify this in Geogebra. Here we are in Geogebra, and again, we've selected the 3D graphing calculator option. If we put in v as a lowercase letter is equal to parens cos t is the x component, sine t is the y component, and t is the z component, you see that we do end up with a right circular helix. Now, let's rotate this around so that we're looking at that first octant to where my positive x's are coming out in this direction, my positive y's are coming out in this direction, and we do see that our right circular helix was starting at the correct point and then moving around the outside of that helix. If we scroll out, we can see a little bit more of the helix, although we're being limited because of the fact that the value of that parameter is only going from 0 to 2 pi. If we come in here to the declaration of where the parameter can go and we let it go to, like, say 4 pi, we'll get to see more of that helix. We're going to let time travel a little bit longer, and we get our particle that travels a little bit farther around the outside of that helix. Let's take a look then at what would happen if we had a different vector function. I'm going to call it w, lowercase, is equal to changing from cosine to sine as the x component, cosine is the y component, and t is the z component. Let's see how that changes things. Let's also change the color of this second one so that it's a little bit easier to see. If we click on these 3 dots and click settings, then we can come over here to color and change it, let's say to red, or maybe to bright green. It's something that's a little bit easier to see. And then let's X that out so that we can get a better look here. I'm going to zoom back in a little bit in order to have a closer look at these two curves. And let's also extend our value of the parameter for that second vector to being 4 so that we have a little bit more of our helix that is being shown. Notice these are two different space curves. They're starting at two different places, their orientation is different, but they do both have a circular projection in the xy plane. The relationship between x and y is a unit circle.